Good afternoon, ladies and gentlemen. Welcome to IVUESTE 2022 warm-up, the online technical conference preparing to IVUESTE 4th edition. First of all, let me thank you all for coming here today. Let me introduce myself. I'm Virginia, one of Oval Campus organizer. The topic of today's presentation is the development of an up-to-date quality standard for land pickings. The last minutes of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Ralph Vogel, Technical Director at the European Steering Association. Thank you so much and have a good presentation. Ralph, you can start.
Good afternoon, ladies and gentlemen. I'd like to welcome you to another paper at the Industrial Valve Summit. This presentation, called Development of an Up-to-Date Quality Standard for Gland Packings, was created by my fellow technical director at European Sealing Association, David Edmund Scott, and myself. Some biographical information about myself. My name is Ralph Vogel. I'm a mechanical engineer, and I've been working now for over 26 years in the sealing industry. Currently, I'm the full-time technical director of the European Sealing Association. Before, I worked as Group R&D and Engineering Manager for Bookman Packings GmbH. Here, basically, my main tasks were R&D of packings and gaskets, as well as application engineering, including also fugitive emission solutions. I worked quite a lot with also with end users and valve OEMs on application engineering problems and gained quite a lot of experience solving problem cases. Some information about the European Sealing Association. The European Sealing Association is a trading organization of European-based companies which manufacture fluid sealing devices. It has been established in 1999 and is registered in the UK and Germany. The main sealing groups we represent are mechanical seals, packings, gaskets, elastomeric and polymeric seals, and expansion joints. The ESA has around 50 members, including also research organizations and universities. We also work quite closely together with a similar organization in the US, the Fluid Sealing Association, which represents all the sealing manufacturers in the Americas. Fugitive emission performance and long service life are key requirements for modern braided gland packings. But when deciding which packing to select, there is no overall recognized standard to define the quality of the packing and the material used in the packing. There are some emission performance standards like API 602 or company-related standards like Shell MESC 85-204, but they define only specific performance requirements. The quality of a packing and its materials can guarantee a long service life and a good performance. But by saving on the seal costs, some low-cost materials might not meet a certain quality standards and are likely to fail prematurely or suddenly. In this case, quite significant costs can arise due to product loss or downtime, as seen in the pyramid in the picture here. Also, other related costs like environmental or legal costs in case of personal injury or environmental damage can be quite high. There's an old British standard in existence to define quality aspects of a packing material. It is BS 4371 from 1999. But this standard has not been maintained, is now very outdated, and it does not include modern packing materials. It even still describes asbestos materials which have been long banned in the European Union. The members of the Packings Division of the European Sealing Association and the Fluid Sealing Association have developed an up-to-date specification for gland packings, defining good material specification. In the following, I will give you more details about this new standard. A specification for gland packings manufactured from yarns and ribbon has been developed by the ESA and the FSA over the last 3 years. Now the final draft for the packing material standard has been approved, and this specification provides a method of describing the materials, the impregnates and lubricants for various types of yarn and ribbon-based packings intended for use as gland seals in mechanical equipment such as pumps and valves. In the first part of the specification, the yarn groups and materials are defined. There are 6 categories, including natural yarns, glass, ceramic, synthetic, PTFE, and carbonaceous yarns. In the group, the most common materials are listed and they are given a yarn code for identification. So, for instance, in the natural yarn group, there are rummy, cotton, flax, hemp. In the glass and ceramic group, there's glass, ceramic yarns, and mica. In the synthetic fiber group, there are pararamid, metaramid, acrylic, polyamide, novoluid, PPS, and PBI yarns. The PTFE group contains PTFE filament yarns, as well as ePTFE, ePTFE graphited, ePTFE graphited and oil, as well as ePTFE filled with talc and oil. The last group is the carbonaceous material. There we find the pre-ox pen yarns, as well as the carbon and graphite-based yarns, and the expanded graphite yarns. In the next material group, the typical impregnants and lubricants used in packings are listed in a separate table, and they also receive an associated code. It can be basically that there's packings using no additional impregnant or lubricant, but the main ingredients added into a packing are PTFE, mineral grease or oil, silicone grease and oil, graphite and mica as impregnants or lubricants. Additionally, the packing or the packing material can be also reinforced, and also for the type of reinforcement there's a separate table listed and coded again. So there can be no reinforcement, or glass, cotton, carbon, PTFE filaments, stainless steels, or Inconel can be used to reinforce the packing material. Important characteristics for the good quality packing yarn are the tensile strengths and the elongation and break values. In the standard, the table has been defined with minimum values here with the help of yarn manufacturers to make sure that the packing yarns will perform and that the packing can be produced and braided without any problems, as well as guarantee that the packing will perform in the application under elevated temperatures as well as pressures. Another quality criterion for packing yarns is the shrinkage value, especially at elevated temperatures. A table here has been also created with the help of manufacturers to show certain shrinkage values or maximum shrinkage values in air at elevated temperatures. Especially, for example, low-quality PTFE yarns, not properly pre-stretched, can show significant shrinkage and failure in service due to extrusion and related high gland pressure losses, but also with other materials which show high shrinkage, problems can occur and the service life will be shortened. Another quality criterion for packing performance is the creep relaxation under gland pressure. Unfortunately, for specific packings or packing materials, there was no specific creep relaxation values available. So the packing division decided to run their own test, and one of our members is the company Amtech Messaging Service, who's specializing on testing of packings, gaskets, as well as valves. So we set up a test, and 16 of the most commonly used packing materials were defined and provided by different ESA members. The creep resistance of a single packing ring was established under an initial load of 25 MPa. The test duration and the holding time was 4 hours at room temperature. In the graph here you can see one of the test results. So the packing was submitted to the 25 MPa, then there was a short holding time, and then it was retightened to 25 again, and then the relaxation or the gland pressure loss over 4 hours was measured. And also after finishing the test and when the rings were extracted, the extrusion was checked. Based on the test results, minimum creep relaxation values have been determined and put into a table, which you see here on the right hand side. The table shows the different packing types that have been tested. We start with rummy, PTFE and all, cotton grease packings, para-aramid and meta-aramid, both with PTFE and oil impregnation, acrylic, PTFE and oil, polyamide, PTFE and oil, novolit, PTFE impregnated, PTFE filament packing with a PTFE impregnated dispersion, ePTFE, and the different type of ePTFEs, graphited, graphite with oil, and talc and oil, and then the carbon-based packings like Preox-Pan with graphite PTFE impregnation, carbon filament with graphite impregnation, graphite filament, graphite impregnation, and expanded graphite reinforced with Inconel. You see the difference here in the creep values for the typical pump packings who contain grease or lubricant as the running in lubricant. These values are quite low because again the oil will run out under pressure, which is intended for pump packings to counteract the heat dissipation. For the valve packings we have significant higher values, which really starts for PTFE with creep values bigger than 75, or for carbon filament values bigger than 80%, and with expanded graphite reinforced with Inconel we have values that's even bigger than 90%. Besides the specific values that have been shown in the previous slides, other criteria are also defined in the guideline. For example, for the pump packings, again, the grease, oil or binder content, because this shouldn't be too high, because again, a high amount of grease, oil and binder will give a quite high creep relaxation or volume loss, and the packing won't last that long in the application. Then again, the dimension and tolerances are defined that a good quality packing should have, because that's important to install it without any problems. And also the packing density and tolerances are given, because again, certain density values for packing will make sure that sufficient impregnation is in the packing. Also, in addition, there are certain guidelines given for the packaging and the marking of the products, which is also important to protect the product and when it is stored to make sure that it will maintain its storage time. Some of the packing criteria mentioned in the standard, international standards or guidelines are already in existence. They are all referenced in the document. But then again, we also produced a quite extensive appendix for test procedures that had to be defined to make sure that the quality standards can be met. So the first one is the determination of the grease, oil or binder content, the determination of the size, the determination of the density, and again, the tables shown in the previous slides is the determination of tensile strengths and the location at break of packing yarns, the determination of shrinkage of the packing yarns, and the determination of the creep resistance of the packings. They all have been defined in an extensive appendix, and the specific methods are given. To sum up, a new guideline to define good quality packing materials as well as packings has been established and approved by ESA and FSA packing division members. It has been forwarded now to SEN as a new work item proposal to establish an EN standard. We hope the proposal will be accepted and we can develop our draft then into a recognized standard which can be used to define good quality packings as well as materials. This brings me to the end of the presentation and I'd like to thank you for your attention. In addition, we have a question and answer sessions where I will be answering some questions in relation to this presentation.
Ralph, here is your first question. What is the benefit of this standard for the valve OEM or end user?
The benefit of the standards for valve OEMs or end users is that they can be sure that they buy a quality product which is defined in the standard. For example, values like tensile strengths, shrinkage, creep relaxation determine how good the performance of the product is and if it will be guaranteeing a longer service life and a good leakage performance, which is important nowadays, especially in regard of fugitive emissions.
Ralph, is the standard only for valve packings?
As mentioned before, the standard is not only for valve packings, but also for pump, mixer, or agitator packings. The difference is the pump or mixer packings have a running-in lubricant, which guarantees that the heat expansion at certain shaft speeds is counteracted, whereas the valve packings only contain an impregnation to make sure that they have a good leakage performance and low creep relaxation.
What is the timeline to see this standard adopted as an official chain standard?
The timeline to see this standard hopefully adopted as an EN standard is quite long because there are several stages that the standard process has to go through. It will be probably around 3 years after the initial proposal stage. There's a preparation stage and then a committee stage. Then it will be inquiry stage and it will be voted upon. And if it finally will be approved, there's an approval as well as a publication stage. But we hope in around 3 years that this packing standard will be published.
Ralph, your next question is, Can this standard help to guarantee a longer service life for a packing?
Can this standard guarantee longer service life for packings? I believe so, because again, certain quality criteria that a good packing should have to maintain a long service life, less leakage, are in the standard, as I described before, in regard of the tensile strengths, the shrinkage, creep relaxation, and other quality criteria for the packing products.
Thank you, Ralph, for your guided presentation. The time is over.
I'd like to thank you for your attention.
I wish you all a very nice day. Bye bye. Good afternoon, ladies and gentlemen. Welcome to IVS 2022 warm-up, the online technical conference preparing to IVS 4th edition. First of all, let me thank you all for coming here today. Let me introduce myself. I'm Virginia, one of our campus organizers. The topic of today's presentation is Kodak's top entry butterfly valves with low fugitive emission and improved cryogenic sealing technology in several thermal cycle and endurance tests. The last minute of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Patrick O'Facker, Managing Director at Codex Zero Leakage Butterfly Valves for Server Service. Thank you so much and have a good presentation. Patrick, you can start.
So, hello everyone. Today I'm presenting the topic Kodak's top entry butterfly valves with low fugitive emissions and an improved cryogenic sealing technology in severe thermal cycle and endurance test. I'm happy to have this opportunity today and thanks to IBS Industrial Valve Summit that I have the chance to do this presentation even when it's now virtually. But better than nothing, we hope to see us all soon in a real conference and can have conversations. But for now, it's a good way to stay connected and to present current developments and topics. My name is Patrick Hofacker. I am Managing Director at Quadax in Germany. I do have a Bachelor of Science in Engineering Economics, and I work since around about 12 years now in the valve industry. Yeah, Quadax for offset butterfly valve is a German company. We are located in Feuchtenberg, which is a little village in southwest of Germany, and we do belong to a bigger group which is called the Müller-Coax Group, a company that has a tradition of more than 60 years now with valves for a lot of applications, and especially in high pressure applications. And you can see the picture of the plant here in the valley on the right side here. So with this slide, I thought about how can I give you a virtual impression of the Müller-Coax Group, and thought the best way is to just show you the image video on this slide. So I hope you got a nice impression of the Müller-Cox Group, and I think you saw that we have a very high vertical integration in our production. We do a lot of things by our own. That's the only way we can control the highest quality, which is our aspiration, because we deliver valves for the most extreme and demanding applications, and the safety aspect is on top of everything. So our strategy is clear to say we have a centralized production where we can keep every single quality step and production step under control. This doesn't mean that we are not global and worldwide, which you can see on this slide. So even if we are very centralized from a production standpoint, we do have these days more than 5 subsidiaries globally in the USA, in Singapore, in the UK, in Spain, Italy, now also in the Netherlands, and we are present in more than 28 countries with long-term partners, distribution companies that are working with us very closely. Yeah, so now you get an overview over the company, and now we come into the technical topics, design, construction principles, and then sealing technology, which is the big point of this presentation. But yeah, with this slide, I want just to give you an overview of the evolution of butterfly valves, starting from centric to single offset valves, which are mainly ball valves, not butterfly valves. And then the double offset butterfly valves were developed, and then latest triple offset butterfly valves. And now Quadax is coming to the market and saying they have a 4 offset butterfly valve. So a lot of people are asking what is behind this 4th offset, and that this is what I quickly want to explain, so I don't jump over every of those steps, but I want to show you the difference between the triple offset valves and the 4 offset valves, because at the end this is a big factor on this improved sealing technology that Quadax has. So the conventional triple offset valves, and this is what you can see here. There is a round output cone, which is here turned to the outside. And I show you with this little red tool here that the clue of the triple offset valve is that we have one side a straight side on the sealing area and one side an angle side. And that was the very clever development that made it possible to construct or design a butterfly valve with totally metal to metal sealing. And therefore, butterfly valves were able to go into higher demands, higher temperature ranges, and higher pressure ranges, which was not possible before. These applications were solved with gate valves or ball valves and not with butterfly valves. But butterfly valves have the advantage of being very compact and coming to bigger sizes, also less cost intensive. So this was a very interesting development of coming into higher demands. But how did Quadax come to the point to say we develop a 4 offset butterfly valve? Yeah, the reason of innovation is always identifying problems and trying to solve them. And the core problem was that we talked with a lot of customers in the cryogenic applications, and they had issues with triple offset valves leaking in cryogenic conditions, or mainly with high delta T values from ambient to cryogenic state, and this quite a lot of times. So we thought about that problem, and we thought about why does this happen, and our finding was that the triple offset valves work with an elliptical seat and sealing geometry, and therefore the material thickness all around are not the same. And this means when we have high delta T's, the material is shrinking and expanding not exactly in the same dimensions and directions, and therefore it comes to leakage. So the goal of our innovation department, R&D department at the Müller-Cox Group was to design a butterfly valve which keeps the structure of one side a straight, say one side an angle side, to reduce the friction to almost zero, but also have a totally round sealing geometry to have the same wall thickness all around and to be able to use totally round Inconel O-rings and sealing technologies. And yeah, and Quadax did thought about this, and so here's a video that shows you exactly this topic with a cone, that Quadax had the clue of using an elliptical output cone and cut this elliptic output cone under a specific angle. And then we received this totally round geometry by still having one side a straight side and one side an angled side. Yeah, so what are the advantages of this round sealing geometry? Higher CV values, totally friction-free design, lower driving forces, and therefore lower actuation, which is possible. And the result is that, we have the highest tightness. We can work in extreme conditions. We have a homogeneous expansion and shrinking of the sealing material. We have the lowest leakage rate on the market with butterfly valves. We have the highest safety, and we do have a very cost-effective valve. To show you the official tightness ratings here quickly, we have the ISO standard 5208 or EN 12266-1. We do have the API 598. We do have the ANSI classes. And Quadax complies with the highest standards. So on the ISO side, we are rate A, no visual detectable leakage for the duration of the test. Or looking onto the ANSI side, we are even better than Class 6 because Class 6 is still allowing some sort of leakage. And to give you some input that the design is proven and it's not only theoretical input, I wanted to present you a success story of the biggest LNG terminal in Europe, because they literally had those issues with triple offset side entry valves that were leaking due to the cryogenic state and mainly due to the delta T, so to the cycling between minus 196 and ambient temperature. The customer required 42 cryogenic top entry valves, class 150 rated, sizes from DN80 to DN900 or 3-inch to 36-inch. And the best way to show you this top entry design and which application and what are the advantages and about our testing, I show you our latest video for these cryogenic top entry valves. Here we go.
Quadax, made for the extreme. Outperforming top entry valves for LNG. Natural gas is often described as the cleanest fossil fuel. Therefore, the demand for LNG and its importance is steadily increasing for many countries that want additional sources for their energy supply. At LNG terminals, the imported liquid natural gas is unloaded from gas tankers in special berthing facilities at a temperature of minus 162 degrees Celsius and stored in large LNG storage tanks. Before it is delivered to the transmission network, the liquefied gas is smoothly warmed up and transformed into gaseous state. The valves are critical components at each stage of this process. The regulatory requirements are stringent, focusing on the specifications for welding connections in the pipelines. Cryogenic and high-temperature welded valves must be designed to enable maintenance of the internal components without removing the valve body from the line. Two solutions are available. Side entry design. Maintenance is difficult for sizes below DN 300 12-inch. For large sizes, maintenance personnel have to enter the line to replace sealing components. The shaft bearings cannot be replaced without removing the body from the pipeline. Here, the trim cannot be extracted. Extraordinary safety measures have to be put in place. Safety first with a Quadax top-entry butterfly valve. The central top flange can be removed and an efficient replacement of all parts including shaft bearings is possible in a safe environment, and easy access for service personnel is facilitated regardless of valve size. The Quadax top-entry butterfly valve is more compact and lighter compared to other valve types such as gate valves or ball valves. A drastic reduction in weight, especially for larger sizes and valves with higher pressure ratings, allows for simplification of the entire piping system and a subsequent reduction in the costs associated with piping supports. In contrast to the elliptical sealing geometry of a triple offset butterfly valve, the Quadax has a completely round seal. Because of this innovative valve design, the Quadax valve has the following benefits: higher CV values, total round tightness seat, friction-free, has no wear on the sealing area during the closing movement, and a homogeneous expansion and shrinking of the sealing materials. This is the reason why Quadax is the most suitable design to handle easily extreme delta T and keep the tightness longer. Quadax outperformed in the most demanding test on the LNG market, which was based on the requirements of Europe's biggest LNG import terminal. The end user stipulated a test with 10 thermal cycles, combined with an endurance test with 500 mechanical switches. To meet this requirement, a Quadax 4-offset butterfly valve with the specifications DM 500mm and C-Class 150 was tested at the ITIS test laboratory in the Netherlands. The Test Institute ITIS BV certified that the seat leakage never exceeded the low value of 590 milliliters per minute, and after 500 cycles, zero leakage at all was detected. The fugitive emissions were well below the norm and hardly measurable. The benefits in a nutshell: 100% tightness, higher CV values, meets international standards for approval, wide temperature range, reduced maintenance costs, safety for your staff, lowest fugitive emission on the market, lighter and more compact. The Quadax 4-offset butterfly valve excelled in the most rugged test in the market, outperforming industrial standards requirements, providing clear evidence of its quality and reliability in LNG installations. Our innovative butterfly valves are produced in state-of-the-art, fully equipped 5-axis machining facilities. Quality, expertise and experience are the hallmarks of our production process to bring you products that are 100% made in Germany. Quadax top-entry butterfly valve with zero leakage in severe thermal cycle and endurance tests.
So welcome back after this top entry video. I hope this gave you a very good insight about the top entry valve, the sealing technology, the testing, the results, and everything. Now 2 slides that are just underlining and summarizing what was shown already in the video. And this is that Quadax really had the best values of leakage, looking on those 10 thermal cycles that we were going through from ambient to minus 196 10 times. We never exceeded those very low values that you can see here on this side. And here you see the leakage rate which was allowed. And this shows our very, very proven design of cryogenic sealing technologies. The same thing here in the endurance test. You can see here on this slide the leakage rates, and you can see here on top the maximum allowable seed leakage rate according BS C64 for a DN500 valve. And you can see that the Quadax valves on the mechanical switches test were far below the limits, and at the end, zero leakage was detected at all, which was the best results that was ever achieved from a cryogenic butterfly valve. Here's some pictures of the testing in the Netherlands. And here a quick overview over our sealings, because we talk about sealing technologies here. Quadax uses for standard seal, we use laminated graphite or laminated stainless steel, depending on the application. And sometimes we have customer specific or designed sealing technologies, usually for the highest demands and also for these cryogenic applications that we're talking about today. We do use the Inconel O-ring. We can go from minus 270 degrees C up to 800 degrees C, and we can work with very high delta T's. We also do have valves installed for liquid helium applications in the aerospace industry, where our valves work perfectly at these very, very low temperatures. Another design feature that helps us to go in these extreme or severe applications is the sealed bearing design. And with our sealed bearing design, we are able to handle higher pressure values, and we have less temperature limits than some competitors. Here to prove again our cryogenic sealing technology, we did perform another test for a big company that is building globally air separation units. And here you can see the exact same thing. It was a test according BS 6364, and Quadax had zero leakage detected at this testing for this end user. So yeah, why Quadax? Cryogenic sealing solution, cryogenic applications. What is the Quadax solution finally? We do work with stainless steel, CF8M or CF3M materials, usually with welded valves, butt weld or top entry. We do have an Inconel O-ring sealing system, the packaging fixed on the top of the extension. The valves are oil and grease free assembled, and we do work with shaft extensions, customer defined, depending how far away we need to bring the actuator from the temperature or from the valve. And the main advantages are we do have a totally friction-free valve. We do have a homogeneous expansion and shrinking, even when it comes to high delta T values. The valve is basically maintenance-free, but even if a maintenance occurs, we do have free access to all internal parts very easily due to our top entry design. We do have the highest precision in manufacturing in Germany, which gives you safety and the highest quality levels, and we can reach applications with temperatures below minus 250 C, as we can show and prove with liquid helium applications in the aerospace industry. Yeah, a summary of the benefits of Quadax valves. Due to our valve, you will have a increased operation safety. We can go work with extreme temperature ranges. Due to higher CV values and lower actuation, we can reduce the operating costs, and we have a superior and longer tightness and more safety. Here in quick overview over our product range, from lock and wafer version to butt weld, double flange, gate valve replacement. So this one was designed to replace a gate valve, and the end user does not have to do any modification on the pipe. And the latest development is our top entry valve for mainly cryogenic applications. Yeah, Quadax, we do comply with the highest global quality standards, and I don't want to go into detail of all those norms and standards, but we do comply with the highest ones, as you can see here. And if there is something you cannot find on this slide, just simply get in contact with us, or check out our website. Yeah, we talked a lot about cryogenic applications today. Quadax is, of course, present in a lot of other applications with our valve. We do work in the power generation, in district heating, technical gases, oxygen applications in air separation units, thermosolar plants, LNG, LPG systems, refinery, petrochemicals, everywhere where we need safety in severe applications. And there, Quadax is the best solution. Yeah, this was it from my side. Thank you very much for listening to my company overview, talking about our cryogenic sealing technology and our success story and our proven results. And I'm looking forward, of course, to see you next year in Bergamo live at the conference, not here virtually. Yeah, I think now we do have a little Q&A session, but for the presentation, this was it from my side. Thank you. Have a nice day. Bye-bye.
Patrick, where do you manufacture the Quadax valves?
Yeah, thanks for asking, Virginia. As I stated at the beginning of my presentation, we do manufacture the valves 100% in Germany at our factory. The reason is, as I mentioned in the beginning, this is the only way how we can control every single step and have a 100% quality focus that brings us in the position to deliver the highest quality valves for the most severe services and the highest demands.
Patrick, what is the secret behind the furth offsets and why does the design principle give a better thickness?
Yeah, thanks for asking, Virginia. This is a very good question, but I don't think basically it's a secret because it is a clear design difference to the triple offset valve. We did improve the conventional TOV, that's all, for severe service applications by using an elliptical output cone instead of a round output cone, and cut this elliptical output cone under a specific angle. And with our 5X production center, we are able to produce this latest seat and sealing technology on the market to go into even higher and extremer applications than with conventional TOVs, with more safety and even improved and better performance to set the new state of the art.
Your next question is, how many references do you have in cryogenic application?
Well, we do have a lot of references in the cryogenic market because our valve was focusedly developed for cryogenic and severe applications. Um, our reason for innovation was that a lot of TOVs have issues in high delta T's or cryogenic applications. So from the beginning, we designed a valve with end users and EPCs that were focused on cryogenic. So yes, we do have a lot of references. I don't want to share now end user and APC's name here at this stage, but if anyone is interested, he's always welcome to send me an email, to contact us, and we will share specific references in the industries.
Patrick, why are the valves such a critical component in a server service?
Well, the valves are controlling the flow and are always in contact with different medias, and therefore they have to substand several pressures and temperatures and extreme conditions. And when it gets more and more extreme on temperature or pressure sides or particles or specific applications, it gets more and more tough. And sometimes when it comes to nitrogen or liquid helium, it gets more and more safety critical. and you can also not easily measure fugitive emissions with helium. So having valves that are 100% tight and safe and tested and proven is very important for EPCs and end users to have a safe plant, and it is also a big point for a greener planet, and to have less fugitive emissions, and therefore a better global CO2 footprint.
Thank you, Patrick, for your good presentation. The time is over.
Thank you.
I wish you all a very nice day. Bye-bye. Good afternoon, ladies and gentlemen. Welcome to IVS 2022 warm-up, the online technical conference preparing to IVS 4th edition. First of all, let me thank you all for coming here today. Let me introduce myself. I'm Virginia, one of our campus organizers. The topic of today's presentation is a fugitive emission addressing the challenge. The last minute of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Mr. James Simpson, Segment Manager, Oil and Gas Europe. Thank you so much and have a good presentation. James, you can start.
So, my name is James Simpson. I am the Segment Manager for Trelleborg Sealing Solutions on energy and oil and gas. And I'm based in Aberdeen in the UK, having been involved in supporting the energy sector for over 22 years now. The past 14 years have been with Trelleborg Sealing Solutions, and have been in several business development roles. Currently, I work with our sales teams and manufacturing centres across Europe and Middle East, helping to develop business strategies, aligning group goals and objectives in accordance with the industry and customer trends. So today it is my great pleasure to be discussing the challenge of managing fugitive emissions within the energy sector. And to take you through today's agenda, I think I'm going to start with the key question of why fugitive emissions are so important, and looking at some of the drivers that are changing the industry right now. Then we can review the definition of fugitive emissions and expand a little bit on the areas of interest that we are interested in today. Then I want to discuss some time reviewing the key standards in place, giving particular attention to those that are applicable to the United States and European markets. I'll then discuss some of the current solutions that are in use and the associated advantages and disadvantages, before we then look at some of the testing data that we have at Trelleborg. And finally, I'll review the next stage developments and what we're going to do next, and where we need support from yourselves in developing solutions to take the industry into the next generation, into the future. So, firstly then, let's address the reasons why this challenge is so important to our industry. And our market research data tells us that, at an estimate, the global valve market is going to grow over the next 4 years to approximately $10 billion. It's massive. And control valves will be an integral part of that market, growth reaching demand in excess of 13,000 units across the same period. So for us, it's really encouraging to know that this is a growth sector. And the energy industry is going to play a key part in the growth of that, with a variation of valves utilised across every stage of production and processing of the energy industry. But this is an area that has been put under increased scrutiny in recent years as governments and organisations look towards a more sustainable future and strive to achieve zero emission targets. And the USA was certainly among the first to identify an issue with emissions being released from processing facilities. And as you see on the slides here, there is an often quoted study from the Environmental Protection Agency in 2019, which estimated that 300,000 tonnes of emissions were being released from chemical plants each year. And in the same study, several emission sources were identified, but as you can see, by far and away the largest factor is valves themselves, which account for 60% of all uncontrolled fugitive emissions into the atmosphere. And this led to the Environmental Protection Agency in the US introducing new standards for valve emissions on all downstream facilities. And while those may have been rolled back a little bit in the previous years, the current incumbent in the Oval Office is certainly much more stringent on the issue and is already at the forefront of activities to reduce emission levels across the industry. The EU itself, of course, is not slow on the uptake, and they're gearing up to introduce new legislation as part of their target to cut greenhouse gas emissions by up to 55% from 1990 levels and to achieve that target by 2030. There's an EU Commission that are finalising a review of legislative actions. One of the areas they're considering adopting is a United Nations Economic Commission for Europe best practice guideline for monitoring, reporting and verification of emissions within the oil and gas sector. And this best practice guideline and report is far more wide-ranging than what we've seen in EPA, and targets a greater monitoring of upstream facilities as well as downstream production. And also as part of that study, the EU are looking at applying a lot of these directives to any external supplier of energy products to the EU as a whole. So that would mean that any regulations that are introduced by the EU may be adopted in locations far outside typical EU boundaries as best practice. Within the energy industry, of course, we see liquid natural gas production becoming a major growth area within the industry as both an economic and cleaner fuel supply than typically coal or oil. And combined with its capability to be incorporated into blue hydrogen production processes, then natural gas is seen as a very viable solution for energy production. But again, and there's always a but, there is a focus to ensure that these new developments are also made sustainably, and there's a greater interest in the CO2 emissions on such facilities across all aspects from production, transportation and processing. And while IOCs look for growth and external investment on these projects, their investors are keen to be investing only on projects that meet their own sustainable goals and can be presented as such to an outside world that is definitely monitoring these things far more carefully than a few years ago. Okay, so we know that this is an important issue and it's going to be a major consideration on future energy developments. But what exactly are fugitive emissions? These are any chemical in a physical form that can unknowingly leak from an installation or pressurized equipment, primarily from industrial processing or production facilities. And these fugitive releases contribute to air pollution, and depending on the gas involved, they can be very dangerous to any human personnel that are either operating that equipment or simply just working nearby. And so as a result, all equipment within processing facilities can be tested for fugitive emissions by trained test engineers. And this can be done as part of an OEM assessment on equipment at manufacturing stage, as well as a monitoring program during service life. And what we find now is operators and OEMs will frequently ask manufacturers to provide a valve design that has been tested and proven to meet a very stringent level of emission. And these can be tested using methane gas in line with the United States Environmental Protection Agency requirements, but can also be tested with helium gas, which has a much lower molecular weight and provides a much sterner test of valve capabilities. However, any valve has got to prove to be a leak type within the pressures and temperature parameters designed to operate within, and leakage rate can be monitored in various ways depending on the standard. The primary leakage area in any valve is going to be the stem arrangement, and this is where the valve is connected to an external actuator, and movement of the stem during opening and closing the valve can allow leakage. This area will contribute to 80% of all valve leakage, so it's no surprise to us that this is the area where the various standards concentrate their efforts on. And there are a variety of standards that can be adopted for testing. And some are set by the international standards organizations, such as American Petroleum Institute and the International Standards Organization themselves. Other tests are specified by particular end users, most commonly being maybe one by Shell, which is specific for their own facilities. And for us, and for what we were doing, the most interesting ones are the more wide-ranging international standards, which could apply across various different facilities. We can have a brief look at these. First up is the American Petroleum Institute, and they have 3 standards for low emissions on valves. And these really are focused on low pressure downstream valves with prescribed testing set at ambient temperature 260 degrees C and 41 gauge bar operating pressure. So that in itself gives us a good range of fugitive emission, low emission valves for one particular segment of the industry. Maybe more interesting for us would be ISO 15848, created by the International Standards Organization, which introduces a whole range of variables to the test data and is much more aligned with real applications that we see in upstream oil and gas, where we can test valves at much higher pressures and different temperature ranges, more in line with application conditions. So this makes ISO 15848 perhaps a more interesting standard and one that we want to align our products to. So those are the standards we're looking to achieve. How are emission targets met currently? Well, there's a range of typical options used at present. So alternatively, engineered packing sets offer a viable compromise between bellows and graphite ring solutions. So these are usually manufactured in an arrangement of PTFE or even sometimes elastomer rings, supported by a high modulus thermoplastic material such as PEEK to prevent extrusion. And these components get set into the stem packing gland. A spring energized lip seal can be utilized to preset the seal, and that allows the pressure to assist energizing the supporting rings while keeping low pressure sealing capability and also torque and friction levels to a minimum. By having multiple barriers behind the main spring energized seal, very low levels of interface leakage, the leakage between the seal lip and the hardware, can be achieved. The resultant solution is adjustment free across many cycles. It's compatible with nearly all gas and chemicals and capable of operating at a very wide variety of pressures and temperatures depending on the design. And typically engineering packing sets are suitable for Class B type leakage rate as per the ISO 15848-1 standard with a reasonable service life. But of course, there's very little test data in the market to support OEMs on designing and successfully testing these solutions for their low emission valve applications. And this is the task that Trelleborg have set ourselves going forward, to work in partnership with key clients to deliver validated solutions and good support and information and assist in production of best in class low emission valves for whatever application they're required for. And how are we doing that? Well, in order to begin putting together information for customers, we decided to start off following the API route of creating an initial fixture test to compare different stem seal arrangements in similar conditions. And back in 2017, we completed the first upgrade of our testing capabilities, and that incorporated an electronically controlled environmental chamber matched with a purpose-built test fixture built along valve stem seal lines. And this fixture allowed us to conduct comparative tests at a wide range of different arrangements across a temperature range of -50 to +150 degrees C. But we did have some limitations, of course. First, as you can see, the test rig only really allows for static test on the seal set. And secondly, our pressure rating on the system was limited to only 150 bar. However, that still did allow us to screen test a lot of designs and analyze how low pressure leak type performance across the seal interfaces, which is a key concern in low emission testing. The media selection was, of course, another area of discussion, and we certainly opted for helium media as the preferred option, partly as it provides a more robust test of seal design, but partly, of course, because it's a lot easier to work with. A leakage rate target was another focus, and again we fell back on ISO 15848-1 and selected leakage criteria based on that. As we're conducting static tests on this rig, we really wanted to achieve Class A leak tightness on an engineered pack and set arrangement, if at all possible. And for measuring the exact leakage rate across the test seals and helium, we again looked at ISO 15848 and installed a full vacuum data collection system for a much more precise data collection instead of relying on sniff testing as we've done in the past. So that's our setup, and what did we find out? Well, this is our initial test results conducted using a very basic spring energized seal supported by some graphite rings as an initial control, as a first stage improvement on typical current solutions. So on this graph, what you can see here is a green line, which represents ISO Class A allowable leakage rate for the given stem diameter. A purple line down here, which represents the ISO Class B leakage rate. Our brown line is, of course, our pressure, and the red line is the temperature as it changes, and the blue line is our actual leakage rate experienced throughout the test. So as you can see here, as our temperature starts off at ambient and we have 20 degrees C, we have a very good low-level leakage. As it ramps up to 150 degrees C, the leakage rate remains consistent. We bring the temperature down to -50, and that's where the pressure drops accordingly, and we see an increase in the leakage rate. When the temperature comes back up to 20 degrees C, the pressure stabilizes, the leak rate decreases. And overall, we found that this seal stack performed reasonably well, and certainly well within the requirements of the Class B leakage rate throughout the entire test cycle. But for us and our main target, we were very much aware that at the low temperature, -50, our leakage rate did exceed that required by Class A. So it was a good first test. So next up, our next test was to increase the surface contact area and to review the impact that had on interface leakage between the seal element and the hardware. And we did this by setting several reinforced chevron rings behind the spring energized seal and creating a longer seal assembly. And for comparison, of course, we kept the graphite rings in place behind the stack. And repeating the same test with the same green and purple lines representing Class A and Class B leakage rates, and the same brown bar for pressure and red bar for temperature. Our blue line is our acceptable leakage, our actual leakage rate. We see that once again we have solid performance as the temperature ramps up to 150 degrees C. As the temperature comes down to -50, the pressure comes down. We do see more leakage at the lower temperature. As it comes back up again to room temperature, once again pressure stabilizes, the leak rate recovers. But this test showed that not only did it pass Class B, but while we got increased leakage at the lower temperature, we find that this set came through the entire test well within the parameters of Class A leakage. And this demonstrated to us that engineered packing sets can achieve Class A leakage even at low temperature and pressure, given enough contact area and in the right conditions. Now, we were aware that our successful test incorporated graphite rings as part of the overall stem arrangement, and that did lead to discussions as to whether really the graphite rings are doing all the work here, and whether really we needed to repeat the performance without graphite rings. And yeah, there might be sometimes we want to keep graphite rings in the design, particularly on fire-safe applications, but the purpose of our testing was to prove an engineered packing set can deliver the performance that the industry needs. So to that end, we began testing several design iterations to the same conditions to achieve direct comparisons with our original tests. And without going through all of the individual tests, our results demonstrated that multiple redundancy and increased surface contact provides really good seal performance, and all stack arrangements passed Class B level leakage rates. However, achieving Class A certainly required further development. And fitting higher loaded helical springs to our designs, as you can see on our first three seal stacks there, certainly was a good solution for increasing the level of interface force to achieve consistent Class A leak tightness. But while this is great for a static test and a static solution, we're really all too aware that this might not be as effective on a dynamic application where the stem's moving back and forth. These high load helical seals put a lot of torque and friction onto the design and would ultimately cause premature wear and leave you maybe not so better off. So our next objective was to obtain Class A solution based around typical dynamic solutions that are already in place for high pressure applications using a medium load cantilever spring. And this was achieved by a combination of material selection and spring design, and of course review of hardware conditions to achieve the best results. And the summary of that really at the end of our initial testing is as follows for fixture testing: that we certainly have a range of self-energized low friction stem seal arrangements capable of achieving ISO 15848-1 Class B leakage in typical conditions, and these can be supported by graphite rings if necessary. We also have self-energized low friction stem seal arrangements achieving ISO 15848 Class A leakage supported by graphite rings. And now there are several options for achieving Class A leakage without graphite rings, but given the right hardware conditions, and a few other parameters that we noted during this test. And it's worth mentioning some of these, as they're definitely areas of concern and something that any valve OEM or anybody conducting fugitive emission testing should consider. And firstly, the surface finish is incredibly important for achieving lowest possible leakage rates. And our best results were achieved when we polished our stem and groove walls to 0.1 RA and achieved a bearing ratio in excess of 70%, as shown on the slide here at the bottom, with the optimum RMR and lots of valleys in the surface finish and no peaks. Excessive handling of components prior to installation also has an impact on performance. PTFE materials are very susceptible to scratches of fingers and nails around over the sealing surfaces, and even the most minor running of the seal across the fingers can have an impact. So we recommend keeping components in original packaging right up till the final installation, and certainly recommend that you guys all resist the urge to pick the seal up and play around with it and touch it and handle it before it's put into the valve, as our engineers find out to their cost. So all the results shown so far also we know represent static testing only. So we also think that there's an assessment may need to be made in relation to leak tightness versus endurance class for dynamic operation, because wear on the sealing interfaces will have an impact on the long-term leak tightness of that seal. And that brings us to my next area of discussion, of course, which is where we go next and what our next stage developments are. So we are aware that we need to do more to replicate real conditions in an actual valve to prove durability and long-term effectiveness of our selected seal arrangements in real-life valve applications. And last year, we did a further upgrade to our existing test capability and added much more functionality to our stem seal testing. We've expanded our test vessel so it can take a slightly larger stem seal and different stem arrangements. We've attached an actuator to the rig, allowing for both linear stroke and a 90-degree on-off oscillation. And of course, the vessel is now capable of taking pressures up to 100 megapascals with a new gas booster installed to help us on that. And a custom environmental chamber has been added to allow us to test at temperature ranges from currently approximately -70 to +250 degrees C. And this now brings our test criteria much more in line with actual conditions in valves across the upstream and production sector. So shorter test than an actual valve, this is probably about as close as we can get. And we will be able to assess the impact of stroke speed, clearance gaps, and other valve type variables to the leakage rate and lifetime performance of the stem arrangements. And it will greatly enhance our ability to advise clients on optimum conditions for achieving a successful test within their own equipment. So I've got that in mind. What do I need from you, as I said back at the start? Well, whether you are an OEM designing new valves for the industry, an operator looking to reduce emissions across all processing and production facilities, or even if you're involved with organisations such as EPA or in the EU, we want to hear from you. As I've shown there, we have many variables to low emission valve design and testing. We have limited resources. We can't test for every eventuality. Our testing will be limited to fixture testing, so we can't do a compliant ISO 15848 design in itself. Each valve needs to be validated independently and will likely be tested even in production. But we do want to provide the best advice possible and demonstrate the success of our designs in the right conditions. But the question is, of course, what conditions? Should we be testing in helium or methane? Should we do linear stroke testing, quarter turn? Most importantly for us, where is the compromise between leakage rate and endurance class that best suits the industry currently and in the future? And what pressures and temperatures should we be looking to test that will cover as many of the applications as possible? We need to hear from you to ensure that our test program is as relevant for as much of the industry as possible and gives the best advice. To that end, of course, we've been reaching out to people ourselves and our own customers over the last 9 months since we started the investment in Bridgewater, and we have a few ideas for where we need to start. The feedback so far says that we should definitely be testing in helium. We should be looking for tightness class A and endurance class C01 with a linear stroke. And the feedback is that if we could achieve a low emission leak tight sealing at class AH at 69 megapascals in a temperature range from -46 degrees C to +150, then we'd be in a very good position. But that's what the stands right now. All feedback will be welcomed, and I certainly encourage everyone involved listening to this presentation to get in touch on requirements and ideas and thoughts on where the industry is moving in the future, so we can make this as relevant as possible. So in summary, fugitive emissions within the energy industry are going to be a growing focus in the coming years. New legislation is going to be targeted at minimising CO2 and methane gas in particular, and there's going to be greater monitoring of performance in this area across every aspect of the industry, from upstream right down to downstream. Clean gas production is going to be a major growth area for the energy sector, but it will need to be seen to be clean and sustainable, with zero emission targets being set. There are a variety of standards available for validation and production testing the valves, but for me, it looks like ISO 15848-1 and -2 appear to offer the best criteria for valve manufacturers designing and supplying valves across the entire spectrum of energy production. But of course, even within this, there is a large degree of variation even within that standard. There are several options available to manufacturers to reduce emissions across the valve stem, and particularly related to low pressure downstream applications. However, we believe engineered packing sets offer a viable solution for applications in highly corrosive media, high pressures or low temperatures, and certainly for gaining extended service life for remote locations. Multiple barriers and increased surface contact, combined with hardware surface finish and minimal handling of components, are all critical aspects to realizing the best performance. However, further data is required by everyone in the industry to complete our knowledge and to be able to offer trusted advice to OEMs and operators on successfully reducing emissions. And finally, and perhaps the most key takeaway of all, is that all industry players are required to assist us in putting together, giving us information and assisting solutions providers to design and test effective solutions that will meet the industry requirements today and in the future.
James, your first question is, can we use elastomer solution on fugitive emission?
And that's a very good question. And certainly we do see elastomer solutions on fugitive emissions, and we have some customers that will use a selection of seals of primary and secondary, and perhaps have an elastomer O-ring as a secondary solution in there. Well, I demonstrated earlier that some of the packing sets and chevron sets can be involving elastomer solutions as well. The drawback of using an elastomer solution, of course, it comes with the conditions that the valve have to operate in. Once we introduce an elastomer to the equation, then we have to consider chemical compatibility, compression set, and the temperature class, and the pressure combined with the temperature for low pressure applications. So there are a lot of more questions about elastomers that need addressing when we introduce these to valve sealing solutions. But certainly they can be a solution within the right applications for fugitive emissions.
James, how does the level or torque on packing set differ from graphite rings?
Another interesting question here. So yeah, the level of torque is a significant factor on graphite rings, and it would be a factor of 2 or 3 difference from using a preset engineered packing set. So one where we have a medium duty spring with chevron sets behind it, where it is preloaded and has free space in the gland, will have a much more reduced torque level than having an all chevron packing set or graphite rings, which are physically compressed and forced into the gland.
James, how long before we have more test data on dynamic testing?
Yes, that's interesting, and of course I can't talk for test engineers at this time, but we are certainly in the planning phase right now. We have a little bit of work being done on our test vessel itself right now, which will be completed in the next month or so, and we expect to have some of the first results being reported back in the next 9 months, and perhaps over the next 12 to 14 months we will have a lot more information on the success of the testing process so far. So it's an ongoing thing, and of course with everything, when we've got new test equipment, there can be issues and there can be setbacks, but all in all we do hope to have some new information to present in the next 12 months.
James, your next question is there ever likely to be a leak-tight valve?
Yeah, that's $1 million question, isn't it? A leak-tight valve. Well, you know, the head says possibly not, but you know, never say never on these things. When we have externally actuated valve across the stem, the dynamic movement is always prone to create a certain level of leakage, but you know, there are a lot of operators and of course R&D budgets right now being spent on developing new valves and new valve designs, and with the introduction of electrification to energy production and the reduction in hydraulic systems, that brings another element to valve design. And I would not be surprised to see in maybe the next 5 to 7 years new valve designs that are completely leak tight. And what they would look like is going to be an interesting question. So it might be something that looks completely different from what we see today as a typical valve design. But I do think there are going to be some bright ideas in the coming years, and particularly as the focus on fugitive emissions and the greenhouse gases from energy production becomes more intense. It's going to drive new inventions and innovation in the industry. And I, for one, am very excited to see what comes about in the next few years.
Thank you, Mr. James, for your good presentation. The time is over.
Okay, I appreciate that. Thank you all very much for your time and attention today. I greatly appreciate that. I would like to say a big thank you to Virginia and the team at IVS and Evalve for the ability to give me the opportunity to come and talk to you today. I really hope it has been interesting and insightful, and I really look forward to hearing some feedback from you all in the coming days. Thank you very much.
I wish you all a very nice day. Bye-bye. Good afternoon, ladies and gentlemen. Welcome to IVS 2022 warm-up, the online technical conference preparing to IVS 4th edition. First of all, let me thank you all for coming here today. Let me introduce myself. I'm Virginia, one of our campus organizers. The topic of today's presentation is the sealing solution for cryogenic valves. The last minute of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Christian Salvatori, Business Development Manager, Energy EMEA at Victrex. Thank you so much and have a good presentation. Christian, you can start.
Hi everyone, and welcome to this online technical conference. I am Christian Salvatori, Business Development Manager at Victrex for the energy market. So today we will go through a new family of products recently developed by Victrex, and I'm really pleased to present you the technical benefits of such polymers in cryogenic environments. So the focus will be on having a reliable sealing material in cryogenic valves for the LNG. So just a few words on myself. I have a physics engineering background, and I'm working in the oil and gas since the beginning of my working career in 2008. I started at Schlumberger as a seismic acquisition engineer on board of vessels, rigs in Western Australia, dealing with the data acquisition and processing while scanning the seabed for the research of oil and gas. And then after that experience, I worked for Saint-Gobain Performance Plastics as a sales manager, building a certain knowledge of soft seals for the valve industry until 2016, when I joined Victrex. And at Victrex, I'm focused on various commercial tasks, if you want, and I'm responsible of following various customers, especially in the EMEA region. But what I'm really proud to do is having the possibility of contributing in the development of new materials, either for existing or new applications, working every day to do our best to bring innovation to this market. So here you can see the agenda. The points we are going to cover in the next about 30 minutes is a brief introduction on who is Victrex in energy and what's our mission. Then outlining the challenge and defining the needs in order to have clear in mind which challenges we address. Then we will dive into mechanical and thermal properties of cryogenic peak, putting the CT polymers in comparison with the PCTFE. Selection criteria for the best material. So let's say at this stage, it should be clear enough which benefits you can get by using the CT polymers and what are the differences between them. Then the summary and conclusion, and at the end, I will be more than happy to answer any questions you might have. So, Victrex in energy, we are recognized as the #1 peak expert, either because we invented peak already 40 years ago, but I think even more because peak is the only thing we do. So all the Victrex activities, all the strategies, market analysis, investments, research and development, everything, every single action we make orbit around peak. And how do we act in the market? Well, we think that the best way to serve every market we work in is actually to cooperate with all the supply chain. So in energy, for example, from our direct customer who process the polymer into shapes and parts, to the valve manufacturer who buys these parts for their valves, to actually the end users and the EPCs who needs these valves for their plants. So let's say that staying in touch constantly with the whole supply chain helps us to have a clear understanding of the needs everybody has and to understand the trends of the market and the new opportunities we have to serve the market in the best way, creating new innovative materials and establishing partnerships to develop disruptive technologies. So all of these, including the CT polymers I'm going to present you today, is done with the aim to improve the product performance, for sure. So we understand how challenging your applications are, and we know how important it is to improve and innovate to address these challenges. Then increase the reliability, for sure, providing long-lasting solutions, extending also the lifetime of these solutions, and reducing the maintenance cost as much as possible. This, of course, brings to improve operational efficiency and reduce cost. So just a number, we have calculated that 75 million of peak seals are in use today. This is a huge number. It's just one number indicating how much Victrex peak has been and is now considered a revolutionary material, capable of helping companies who are striving to increase the productivity and to reduce the overall cost. So let's outline the challenge. Let's see which are the issues with the current non-metallic material exposed to a cryogenic environment. So they have a typically high coefficient of thermal expansion. It means that they are significantly changing their dimension as a function of temperature while the temperature changes. So, which is something you would ideally like to avoid or reduce as much as possible when you design a seal, for example. They become brittle at low temperature, risking to break or to get damaged, and this would result into a leakage, of course. So you also don't want this. And there are several ways to test cryogenic valves, and let's say every cryogenic valve is a standalone case, so it's sometimes very hard to achieve certain repeatability of the performances. So there will always be properties, a differentiation in properties. Just to simplify, whenever you have a piece of plastic in contact with a piece of metal, you will have different properties, of course. And having these properties matching as much as possible would be the wish of every valve engineer. So it's clear that a non-metallic seal will shrink at low temperature, becoming less ductile. And both these factors will surely negatively affect the sealing performances of your valve. So either the shrinkage and becoming less ductile, it's a real issue. So this is a challenge for the non-metallic material. So now, PEEK, as you know, is well established on the market and recognized as a material used for high temperature typically and chemical aggressive application. And we know that for cryogenic sealing applications, PCTFE is the only material in use today, also modified PTFE, but let's say definitely more for the static seals or typically for very low pressure. So PCTFE would be and is actually the benchmark. The problem is that today, PCTFE is not anymore capable of covering the increasing range of temperature for the cryogenic valves that the cryogenic valves are seeing. It's become quite common that the end user asks for cryogenic valves which work from -196 to even +200. And consider that 400 degrees is a huge, very wide range of temperature to be covered consistently. So PCTFE is surely a material that doesn't help reducing the torque. It's not cheap and it has certain limitations. We believe that the market would benefit actually of a material capable of doing this. So extending the range of temperature, offering a more reliable sealing, because sealing in cryogenic valves is very, very challenging, lowering the torque, and allowing cost saving. This is something we aimed for when we developed the CT polymers. So let's start with a deeper technical analysis. One important point I'd like to bring to your attention is that the most of the data you will see are at -196 degrees. Why? Because this is where we need to evaluate the performances of sealing materials. So in light blue, you can see the CT100, the first cryogenic PEEK Victrex launched already 4 years ago. And in dark blue, you can see the CT200, the second polymer launched a couple of years ago. And PCTFE is in yellow. So the tensile behavior is what we are looking at because it's a sign somehow of the ductility of the material. So it indicates how suitable it's a material for sealing. While we can see there are no big differences on the moduli at -196, it's possible to actually appreciate a significant higher strength and elongation as well. Significant, especially for CT100. So remember that a more ductile material will result into a more reliable sealing as it penetrates better the metallic counter surface, reducing the gaps and reducing the possibility of creating a leakage path for the fluid you want to seal. So this is a first technical analysis on the tensile behavior to evaluate the ductility, which is actually also confirmed by the next slide, this slide, where again, we have just seen on the graph the values. I apologize because it's quite a tiny graph, so it's not easy to read the values, but it's the same values we have just seen above here. So for the tensile strength, it's around 220 megapascal, and the tensile elongation of CT100 is around 8%, while the tensile strength for PCTFE is around 130 with a 3% more or less of elongation. It's important to underline as well that the elongation of 8% is a lot, because we are talking about almost -200 degrees and everything becomes very, very stiff. So an elongation of 8%, it's really appreciable. So here we see that the way CT100 breaks is completely different than the way from PCTFE, when PCTFE breaks. PCTFE breaks suddenly and pretty fast. On the left-hand side is shown the ability of CT100 to undergo more deformation. Also by looking at the microscope images, you can notice a certain plasticity of CT100. Again, all to underline the ductility of the material, which is very important. It's crucial when it comes to sealing capabilities. Having a material ductile, and ductility is never a simple thing when it's when the temperatures are going so much below the zero. So, as expected, of course, both the CT100 and CT200 offer a higher strength, being at the same time more ductile. So, a combination of properties which become even more important when if you have a relatively high pressure, let's say. So, also the impact strength it's quite important, and you can see that Victrex CT100 had a 4x higher impact strength, while CT200 has a 2x impact strength. So it's either robust, more robust sealing, but at the same time is more ductile. Both of the materials, of course, CT100 we are seeing it's even better than CT200. Now, if we take a look to the compressive moduli, instead, we will notice that the three materials are comparable. So we see how in certain cases we have values 2, 3, 4 times better than PCTFE. For other properties, and like in this case, there are not big differences actually. So, however, as said, sealing performances are a balance of a number of properties like strength, tribology, and besides the mechanical, also the thermal properties, for example. So let's start looking at the thermal properties as well. In this slide, it's shown the second biggest advantage of using CT100 or CT200 instead of PCTFE. So both the materials have in fact a lower and almost constant coefficient of thermal expansion, not only at the very low temperature, but especially as the temperature goes up. So the difference becomes more and more evident when the temperature goes up. So the graph shows data only up to the 50 degrees. The gap with the higher temperature can just increase. So, and we can stop the comparison around the 100 degrees or maybe 120 degrees, where PCTFE is not even usable anymore. So while peak CT100 and CT200 will continue to work properly up to 150 degrees, 180 degrees, 200 degrees, it's of course something depending on pressure. With the same behavior you would expect from a common peak. So there is no changes on the expectations you might have when we are talking about high temperature. So the changes have been made especially for the performances to allow the performances at the low temperature. So we refer to this when we state that CT polymers extend the temperature range of your cryogenic valves and reduce as much as possible any shrinkage or dimensional change. Now, the next slide, we take a look to another crucial thermal property, the thermal conductivity. So the thermal conductivity for both CT100 and CT200 is higher. So as we will never get rid of any dimensional change, what do we want? We want to reduce this as much as possible. But at the same time, we want it to happen as fast as possible. So in fact, the reaction speed of a polymer of changing dimension due to a temperature change is driven by its thermal conductivity. And the higher it is, the faster it will react. So this simply results into sealing consistency, especially while the temperature is going up and down. Your seal will follow its metallic counterpart more rapidly than what PCTFE would do. And this helps to secure your sealing at all times. Again, while for the mechanical properties, we have seen CT100 seem to be better, more ductile and more robust than CT200, we can see that regarding the thermal properties, CT200 is actually the best. And so it's here where CT200 comes to play a very important role, lowering the coefficient of friction, which means lowering the actuation force needed to operate the valve, which in cryogenic valves, it's often a challenge. We listened to our valve customer who were testing CT100 when it was released at the beginning, and they valued so much the mechanical and thermal benefits that this didn't stop us from improving more, let's say. On the other hand, it encouraged us to do more. And so we created CT200 in order to lower the torque and give the possibility to use a smaller actuator. After we released CT200, it was time to collect also data on its performances on field, so on a real valve. So we have started cooperating again with our valve manufacturers and customers to make a comparison test on a real cryogenic valve, stressing the material as much as possible, as much as we could. What you see in this slide is a significant example of testing our material in one of the most challenging conditions. Using a 10 inches top entry ball valve, class 1500s, from minus 196 to plus 120. We couldn't go higher because there was a PCTFE insert inside, and PCTFE cannot withstand, as we said, to temperatures higher than 120 maximum. And we made the TAT test as per the Shell Mask 77300, which allows for very low leakage rates. And we have measured the leakage and the torque. So we have noticed during the test a lower leakage over the whole range of temperature at each pressure. So despite there was some leakage, it was acceptable from the minus 196 up to 120. The test have also shown that the torque in average was lower. So either at 2 bars or 250 bars, so low pressure or high pressure, if we see the torque given by PCTFE is at 1, all the times, all along the range of temperature, we had the lower values. So to summarize, CT100 has an outstanding ductility and sealing capabilities with a great strength. CT200 has better thermal properties and a lower coefficient of friction. So when to use CT100 and when to use CT200, it's actually up to your needs. For example, if you look for outstanding ductility and you want to minimize the leakage as much as possible, probably you should go for CT100. When you want to minimize the torque instead, because you know you can use a smaller actuator, you may choose CT200 in this case. So if you want to reduce the wear, for example, as much as possible, you might go for CT200. If you have already hardened your ball and you know wear won't be a big issue, you might go for CT100. So it's really, it depends. You have seen outstanding mechanical properties for CT100, and you have seen even better than CT100 thermal properties for CT200 and the low coefficient of friction. If you have any question, I will be more than happy to answer your questions.
Christian, here is your first question. You have mentioned the possibility for a cost saving. Can you better explain this point and quantify it?
Absolutely. There are a few factors actually that should be taken into account. The first one is pretty much straightforward, and it's about the cost per kilo of CT polymers, which is in the same range of PCTFE. But considering that CT polymers have about 40% lower density than PCTFE, you simply need less material to get the same number of parts. So, for example, if you have to buy 10 kilos for making a certain billet of PCTFE, you will buy 6 kilos to get the same billet and therefore to have the same number of parts. So this is a simple matter of fact. Another one is more indirect, but not less important, of course, and it comes from the better technological performances. So having a material which lower down the actuation force of your valve, then the torque is lowered down, of course. This might allow the valve manufacturer to use a smaller, so a cheaper actuator, so they can sell a cheaper system. Other things are still linked to the improved technical performances. Lower the torque and lower coefficient of friction are likely to result in less wear or in an extended lifetime, if you wish, which is reducing maintenance cost. So that's why there is the opportunity for a cost saving.
Your next question is, would this material be suitable also for spring-energized seals or other sealing components apart from seat inserts?
Yes, despite the target application is CT inserts, there's nothing against using CT polymers as a jacket material for spring-energized seals, for example. Considering that PEEK jackets are used in the seals market since decades, especially where a relatively high pressure like class 1500 or above characterize the valve. So in these cases, you might combine the robustness of a PEEK-based material with its outstanding ductility and low friction, extending the operating temperature of your valve from minus 196 up to the 180, 200, etc. So absolutely, the answer is yes. We don't have so many data, but of course, again, because we have targeted the CT inserts as the application, every other component which requires the same needs can be addressed with CT polymers.
Are you targeting other applications than valves for LNG for these materials?
So, as mentioned in the introduction, it's well known that hydrogen and CO2 application are already in the radar of the whole energy industry. So today we are moving in the direction of collecting data also at temperature below the minus 196, like for example, minus 253 or even below. This in order to be ready to support our customer regardless if it's a CT insert or any other components in the hydrogen production supply chain. But for sure, we expect our valve customer to ask for support in this sense and that soft materials able to cover even a larger range of temperature.
Christian, what is the composition of CT100 and CT200, and in which form are they available?
Unfortunately, I cannot disclose the composition of CT polymers, but I can say that both of them are a PEEK. So within the family of the polyaryl ether ketones, they are polyether ether ketones. CT100 is an unfilled PEEK. CT200 is a PEEK compound with additives which help to lower down the coefficient of friction. CT100 is a natural color, and CT200 is green colored, which makes it quite unique and distinguishable among the common materials. In which form? CT100 is in granular form, so the typical pellet size you are used to with the common PEEK materials, while the CT200 is coming in form of micro pellet, which is something in between powder, let's say, and the pellets themselves.
Christian, is the chemical compatibility of CT polymers the same as other PEEK on the market?
Yes, absolutely. There are no differences. The chemical compatibility stays the same of the common PEEK you are used to work with. This has always been a must for us, offering the market the possibility of having an alternative material which provides technical benefits at a lower cost, keeping all its other characteristics the same, for example, without compromising on chemical compatibility. So you will get the same identical chemical compatibility you expect and you are used to have with the normal PEEK.
Christian, your final question is, have you performed other tests than the one shown in our presentation?
So we have gone through an intensive and long-lasting testing phase at our Victrex laboratories at some university we work with, and thanks to specific partnership we made with existing customers, either processors or seal manufacturers or seat manufacturers or valve manufacturers, to have a certain repeatability of the results obtained. And the presentation I've shown is the result of this work done in the past year. After this, the material has been released on the market, and in the last years, we have collected several positive feedback from our valve manufacturer who shared successful results with us, which are in line with our value proposition. So we have a list of customers who already tested and validated the material for each size of the valve, from 2 inches up to 24 inches. And also the range of pressure varies from class 600 up to class 1500, for example. So we have proven the quality of the material and how good is the material, and that the behavior of the material is in line with what we expected on paper.
Thank you, Christian, for your good presentation. The time is over.
Okay, so thank you, Virginia, and thanks to the organizers. Thanks to Valve Campus. And should you have any further questions, please don't hesitate to contact me. You should see my contact details here on the last slide. I wish you a nice day and maybe see you soon at the IVS next year in the 2022. Thank you very much. Bye-bye.
I wish you all a very nice day. Bye-bye.